get started. So last time we were looking at time complexity, right? So let me do that example over there. Okay? So what we want to find is, as n tends to infinity, which of these two functions of n grow faster? Okay? So we have two functions, 0.05 n square and the other one is 2n. So we want to find out which grows faster as n grows. So what we could do is you can say if n is 1, this is going to be 0.105 times 1 square, so that is 0.05. 2 times 1 is 2. If n is 2, it's n square is 4. 0.05 times 4 is 0.2. And 2n is 4, then if it's 3, 0.05 times 9 is about 0.45, and this is going to be 6. So on. You go up to 40, you can try for 20 if you want. 20 times 20 square is 400. 400 times 0.05 is going to be 20, right? So this is 20 and this is 40. So you go up to 40 again, then 0.05 times 40 square is going to be 80, and this is also going to be 80. But then once you start at 41, 42 and so on, say 50 and all these things, this is going to be 25, 125, and this is 100. So beyond this point, n is 40, your 0.05 n square is going to start increasing, and then 2n is going to be lower, like I showed in the graph over there. Okay? We were done off. So we're starting the sign up sheet. See that's more better? That's right. Looking good?
It's good. Okay. Probably a little more lighting. It's better.
So, as you see in this graph, after n is 40, you can see 0.05 n square shoots up and 2n is a little more lenient, right? So this is what we want to do. We want to find what's called asymptotic order of growth. Asymptotic always means as something grows larger, okay, towards infinity. So what we can say is our 2n is always less than or equal to some constant times, the constant is 0.05, you can write like that, times n square. For what? It's guaranteed after n is 40 or above, less than or equal to 0.05 times n square, and n is greater than or equal to 40. Right? Clear? So in general, we can write something like this. A function t of n is less than or equal to some constant times g of n for some constant n greater than or equal to some constant n0. Right? So like we have 2n less than or equal to 0.05 n square. Beyond this point, 2n is always less than or equal to 0.05 n square. Right? After n is 40. Like that you can say t of n, some function of n is less than or equal to some constant like 0.05 times g of n for n greater than or equal to n0. If that is the case, then we can say what? T of n is big O of g of n. So this is the big O notation. Okay? So what it means, bounded above. Right? T of n is bounded above by T of n, like 2n. 2n cannot go above 0.05 n square. Right? So we can even remove this constant like I removed here. So in this example, I can say 2n is big O of n square. Okay? So that's the way we represent this thing. Okay? So all always you can see here the exponent, the value of this will be always less than kind of, okay, this is square. Now looking at the other way, what is the other way? Just reverse it. I can say what? 0.05 n square is always greater than or equal to 2n for n greater than or equal to 40. Right? Just reverse the relationship. 0.05 square is greater than or equal to 2n for n greater than or equal to 40. Now I can introduce another notation like this in general. If t of n is greater than or equal to some constant times t of n for n greater than or equal to 40, then I can say t of n is big omega of g of n. So what can you say here? Our n square is big omega of n. Why I omit all the constants? Because I can bring this 0.05 this side. If you want one intermediate step, I can write, we have 0.05 n square is greater than or equal to 2n, right? So I can write what? N square is greater than or equal to 2 over 0.05 times n. So that is equal to n square greater than or equal to 40 times n. So still it is on the form t of n is greater than or equal to some constant times t of n, right? Same form as this. So then I can say n square is big omega of n. So what does this mean? This is like a lower bound. So n square after this point, n is 40. This function is always bounded below by this function. It cannot go below this value, this function's value. Okay? So basically we are finding an upper bound for a function which is denoted by the big O, and then the lowest bound for a function denoted by this omega. Now then there is something in between, right? So we can have a function that is bounded above and below by some other function, right? So let's take up an example for that. So we can have say 3n square plus 2, just to keep it simple. 3n square plus 2 will always be what? If I say this way, 2n square is less than or equal to, this means this is always greater than or equal to 2n square, right? And is guaranteed to be less than or equal to say 5n square. So which means as n grows larger, they grow together. It's just some constant factor or some lower order term is there, but this is the more dominating term. The n square term is the more dominating term. So if you've got a graph, okay, for n and all these functions, we can see again beyond this n0. So after some point n0, this will be our function t of n, right? This will be some constant c1 times g of n, and this is some constant c2 times g of n. You can say this less than or equal to thing. So this is c2 times g of n, this is c1 times g of n, and the middle one is our t of n. So it's always bounded in between. They go together. So I have a good picture here. You see, it is always in between c1 g of n and c2 g of n after a certain point n0. Okay? So in such cases, we can say what? T of n is theta of g of n. So t of n, the function t of n grows at the same rate as g of n. Okay? Is that clear? Any question?
Can you slow down just a little bit?
Okay. If a function grows at the same rate, you see here t of n, right? Like as you see there too, it grows along with it. It's not like the other case where if one grows as n10 goes faster, you see here as n grows faster, T of n is always less than or equal to C times G of n. So T of n is always bounded above. Similarly here it's always bounded below for big O and omega, right? So as n grows faster, if we grow n, this is your T of n, always it is above the C times G of n. So it's bounded above, always by this function G of n. Okay? So if that is the case, it is going to be, you can say T of n is what? Big O of G of n, because T of n is always less than or equal to some constant times G of n. Okay? If it's the other way, which means what? Now I can show you one interesting thing too. So if it's the other way, say this is now what C1, right? Some constant C1, so this is say constant C2 G of n. Then we can say what? T of n is always greater than or equal to some constant C2 times G of n, right? So what can I say with that? T of n is big omega of G of n. So if that is the case, we can also see an interesting relationship. If T of n is always less than or equal to C1 times G of n, and then greater than or equal to C2 times G of n, we can say this is equal to big O and omega, right? If these two things are true, then what can we say? T of n is also theta of G of n. Right? If T of n is big O of G of n as well as is omega of G of n, we can also say T of n is theta of G of n. Okay? But not necessarily. There could be something like what we had, 0.05 n square and 2n, right? Is there any way that 0.05 n square will grow at the same rate as 2n as n grows larger? No, we saw that because as n grows larger, we have n square term here and we have n term here. So always n square term will grow faster, right? So in this case, we can only say n square is omega of n. We cannot say it is big O of n. Clear? On the other hand, the other way, 2n and 0.05 n square. 2n is going to be always, this function is going to be always less than this function as n grows larger. So we can always only say n is omega of n square. But on the other hand, when we had this, as n grows larger, it grows at the same rate as these two functions. The reason simply is because the most dominating term, this n square term, is same as the most dominating term here. It's also n square term. And this is also the most dominating term, n square. On the other hand, the most dominating term, n square, is n square here and is n. So the most dominating term is always going to be greater than the most dominating term on the other side. That's how we compare two functions and say whether it's big O, omega, or theta. Okay? Let's do a couple of more examples. Is it, can I erase?
Yeah, you can write.
There are a lot of empty chairs here. Why you want to sit in the last row? You want to come?
Oh, I can see that also. I can see part of it.
Oh. The others can come.
Yeah, no.
What about, let's do this. N cube plus 3n square plus 2. Now I want to say what is this equal to in terms of theta. I don't want a complex notation, expression. I just want one value, n square, n cube, n to the power 4, something. What should be this in terms of theta? What should go inside? Anyone tell? This is a polynomial and I want to represent it as theta of, like we did there, of something. What could be that? When I say theta, what does it mean? this grows at the same rate. The most dominating term in this grows at the same rate as the most dominating term you want to have here. What's the most dominating term here? N cube. So this should be equal to theta of what? N cube. N cube. Good. That's all. Okay? If I want to write this as big O of something, what can you write this as big O of what? Big O means what? The most dominating term here will be always less than or equal to. Big O means always remember this. This is your t of n. You want always something less than this function. This is your t of n to be less than or equal to some g of n. You want to find out g of n. N to the 4, n to the 5, n to the 1000, anything. Got it? Everyone? You want to write this thing. The most dominating term here is what? N cube, right? That should be always less than or equal to the most dominating term here as n grows larger. So n cube will always be less than what? N to the power 4, right? As n grows larger, or n to the 5, or n to the 6, or n to the 7, n to the 1000, n to the 1 million, anything. Right? So we can say n to the 4. Clear? Any question? Understood it? Now if I want to write it as omega, the same thing in terms of omega, what should be the case? N square. Why? The most dominating term n cube is always going to be greater than n square. You can even write n. Right? You can even write log n. Do you guys know how you compare n with log n? We'll come to that soon. So n square n. Now you see here, if I give this as a polynomial and I want to find some asymptotic representation of it, which looks like more very specific and particular, theta, right? Because as you see here, you can have different values, either n to the 4 or n to the 5, n to the 1000, anything, right? Similarly here you can have n, you can have log n, or even n log n, anything you want. So why now we're looking at like that? Because this could be the time complexity of your algorithm. As we do the time complexity analysis, okay, this may end up being the time complexity of an algorithm, like some expression like this. So I want to write simplistically, either using a theta, big O, omega notation. It is more what? Accurate to say it is equal to theta of something, because then it clearly shows you it grows at the same rate as whatever I write inside the theta. Right? These things doesn't tell you. It just gives an upper bound or a lower bound. It doesn't tell you what's the rate at which your function grows. Your function is this. So it grows at the same rate as n cube. Okay? So that's why in the textbooks for an algorithms or even data structures courses, you would have seen the theta notation more prominently compared to the big O. Sometimes we use big O too, but very rarely we use omega, because omega is always the lower bound. We don't care about the lower bound. So many times, okay? Why this is important? Because you want to find out what's the maximum time your algorithm will take for an input of size n. So that's why we're interested in the theta and sometimes the big O, the maximum limit. You won't go beyond that time. Okay? But mostly you use the theta notation to indicate that the time complexity grows at the same rate as this function inside the theta notation. Okay? Clear? So comparing n and log n, which grows faster, n or log n? N, right? So you guys all know that. So n grows faster than log n, as n tends to infinity. Okay? So what can we say? N is big O, theta, or omega of log n. Huh? can you say about log n with respect to n? Somebody? Big O. Okay? So it's the other way. So always this is true. If a function t of n is what? Big O of g, theta of g of n. The other way you can say g of n is big O of d of n. Okay? It's just the other way. Clear? Anything? Any question? Okay, so now let's try to, like we did here, when I say n cube plus 3n square plus 2, and I just said it is equal to big O of n to the 4 or n cube theta of n cube, right? So we are basically discarding the low order terms, right? And just going with the highest order term, just like n cube, the most dominating term, right? So there's a formal theorem for that. So what is the theorem? So in this course, like I said last class, we'll do some theorem and proving things. Okay? You might have seen that in what? Discrete structures, did you learn some proofs? How to prove things? Right? What are different techniques you learn to prove? Can anyone say? What are different techniques of proving theorems?
Direct proof.
Huh?
Indirect proof.
Indirect proof.
Vacuous proof.
What?
Vacuous proof. Or trivial proof.
I mean the proving strategies. I get something like proof by contradiction,
Proof by contradiction, contradiction.
induction. Right, so we'll be using the contradiction technique several times, sometimes the induction. Okay? So this is a more straightforward proof. If T1 of n, we'll first do G with a big O, and then we can use the theta notation, the same theorem, proof, and then the big omega. If T of n is sometimes instead of equal to, I may use belongs to, doesn't matter, they are the same, so either way it's the same thing. Okay? We'll just use equal to. G2 of n. So if T1 function is T1 of n is equal to big O of G1 of n, and then T2 of n is big O of G2 of n, then T1 of n plus T2 of n is big O of the maximum of G1 of n and G2 of n. Right? May sound a little complicated, but it's a simple thing. What does it mean? Let's look at some example and then we can go further. Let's say we have 3n square and this is say 2n or something. So between 3n square and 2n, which grows faster? Between these two terms, which grows faster as n grows to infinity? 3n square, right? So by itself, this by itself we can say this is some O of n cube, right? And this by itself can be some O of n square. So if I say 3n square is big O of n cube and 2n is big O of n square, and the sum of this is what? Now between these two, n cube and n square, which grows faster? N cube. That's what it is. It's big O of the maximum of these two, which is n cube. Okay? Here, any question? The same thing holds good for theta. Okay? So, can I just change things? Written it. So if I introduce theta here, the same thing holds good. The only thing is, in theta's case, 3n squared is some theta of n squared, 2n is some theta of n. So theta of n square plus theta of n, the more dominating term is n square, so this is theta of n square. That's what we did here, right? When I wrote the theta notation, the most dominating term is n cubed, so I said theta of n cubed. Likewise, we have theta of 3n square plus 2n, the most dominating term is n square term, so it is equal to theta of n square. Clear? And we can extend this to any polynomial of any length. For example, you can have 4n to the 4 plus 5n cubed plus 2, or you can have 7n to the power 9, anything. So in terms of theta, what is this should be? Huh? Which is the most dominating term here? N to the 9. We can omit the constants. Okay? So we'll just say n to the 9. Theta. Alright? So this is for any, it's like we can combine this and this is theta of 9, n to the 9, right? And then combine this with this, the most dominating between these two is still theta of n to the 9 and so on. So the whole thing can be recursively applied. Clear? The whole thing. You can combine these two, the dominating of these two is n to the 9, right? Yes or no? And then this is theta of n cubed, right? So between n to the 9 and n cubed, the dominating is still n to the 9. Combined with this, it's a constant, so it's still theta of n to the 9. So don't think this is just some addition. We can repeatedly apply here like I did. Okay? Yeah?
Yes, sir.
Any question? So we are applying this, right, as a property. Now we want to prove this. How this is true. Given these two, we want to prove that this is true. Okay? So what is given to you? You are given these two. You just use big O. And we want to prove this. Okay? So how do we prove this? So you need to remember, practice this a couple of times until you get it. Because I will ask this in your first quiz or first exam sometime. And remember what I told in the first class, until you show me that you understood something, I'll keep asking you. Okay? Alright, so the topics, the syllabus is smaller, get rid of the difficult things. Don't accumulate the difficult things till the end. Okay? Alright. So, if T of n is, T1 of n is equal to big O of G of n, by definition, what does it mean? What's the definition?
It's a less than or equal to.
Somebody else? Some constant times G of n, right? So I can say this is less than or equal to some constant times G of n. Okay? For what? For some n greater than or equal to, let's introduce some n1, because we have two functions here, right? So for n greater than or equal to some n1, right? Because an n0 is important. For some smaller values of n, it may not be true. Remember that n greater than or equal to n0, after a particular value, it starts shooting up, right? Here? Similarly, I can say T2 of n is what? Same thing, a different constant. Well, I have to have G1 here, right? So like G1 and G2, right? So you have some suffix values here. Suffixes 1 and 2. So T1 of n less than or equal to C1 times G1 of n. Similarly, T2 of n is less than or equal to C2 times G2 of n. For n greater than or equal to n2.